At the International Conference on Open and Innovative Education, Professor Vincent Aleven, Professor of Human-Computer Interaction at Carnegie Mellon University in the US, talks about easy authoring of adaptive tutoring software. Professor Aleven shows us how adaptive tutoring software based on AI technology is capable of adjusting to learners, specifically their similarities, differences, and growth. In this talk, he presents us some authoring tools that non-programmers can use to create adaptive tutoring software easily.
So in this keynote, I would like to tell you about a contribution that my colleagues and I have been trying to make over the past 15 or 20 years, namely a tool suite that non-programmers can use to create adaptive tutoring software. This tool suite is called CTAT, which stands for Cognitive Tutor Authoring Tools, and it can be used to create intelligent tutoring systems. It's grounded in a long history of research and development in intelligent tutoring systems, which are systems that help students in complex problem-solving activities, such as those that they need to do in many task domains to learn to master the material. This system is open. We make the tools available free for non-commercial purposes, so they can be downloaded and used, installed and used. And they're innovative, not so much because intelligent tutoring systems or even these kinds of authoring tools are new, because they have been around for a while, but I think they could be a great source of innovation. They have great potential for innovation if they can bring intelligent tutoring systems to a wider use in a wide range of learning environments, including online courses. And so just to give you a quick preview, this is just an image. I'm not going to explain it, but this is an image of the Cognitive Tutor authoring tools. And as we're using that, we're also using two other open educational resources. One is the Tutor Shop. This is one of the ways in which tutors built with CTAT can be used. Tutor Shop is a learning management system that is geared towards the use of tutors, usually in schools. So it has facilities for teachers so they can assign particular units to their students and they can view reports about how the students are doing. And then a second open educational research, this is not one that I've worked on, but that my colleagues have created, is called Data Shop, which is a very large online repository of educational technology data sets that can be used for secondary analysis. And it has also lots of good tools to analyze those data. And those three things are often used together. So as mentioned, I have not built a data shop, but I've often used it in my research, and my students have used it a lot to analyze data from the tutoring systems to better understand student learning. Because that's actually just as important as building good software for students, is to understand what is hard for them, what is easy, and how well the software is functioning. Okay, but why do we need adaptive instruction and adaptive tutoring software? You may all know that if you look at online courses, then typically they have some reading materials, they may have some videos, and they may have some learning by doing activities. For instance, questions that students answer with feedback, sometimes little problem-solving activities, and so forth. And my colleague Ken Kadinger, who was also at Carnegie Mellon, was interested in finding out which of those two types of activities, so on the one hand the reading and the videos, and on the other hand the learning by doing, contributes most to students' learning. So he looked at data from several online courses and did some regression modeling and came to the conclusion that both reading and videos and learning by doing contribute to learning a lot, but learning by doing contributes 6 times as much to the learning outcomes of students as reading and videos. And so we could ask, if learning by doing is a good thing, how can we have more of it? How can we create good learning by doing activities in online environments? And there are, of course, many possible answers to this question, but I would argue one of the possible answers is intelligent tutoring systems. Systems that can help students with elaborate problem-solving activities. And this is a screenshot of a commercial intelligent tutoring system, the Algebra Cognitive Tutor. And as you can see, so it is a tutoring system for high school algebra in the United States, where students are given some real-world scenario to analyze, have some representational tools such as tables, graphs, equations. And then as they work through this problem in many steps, the tutoring software will follow along, give them some context-sensitive instruction that follows along with how the student is approaching a problem. And the system also tracks their knowledge growth on an individual basis so that the software has a profile of how well each individual student is learning in great detail. And I would argue that there is a nice niche for this kind of software in online and blended courses. So if you look at the kinds of problem-solving activities that are often in those courses, and we arrange them from less complex to more complex, I would argue that you mostly see three types of activities focused on learning by doing. So one is multiple choice questions, often with some feedback from the system. Then there might be somewhat more elaborate problem-solving activities, such as like mixing and matching to line up different categories of things. And then on the other end of the spectrum, there is often in online courses or MOOCs, we see these more elaborate little projects where that cannot be graded automatically by the software. And one solution that has worked quite well is to let students grade each other, so do peer grading. So those are the activities that are often found in online courses, but I think it leaves room for intelligent tutoring systems, which I think slots in nicely in that open spot there. So there are more elaborate activities, more elaborate problem solving that students can do, often with multiple solution paths. But the nice thing is the software can help students for the most part. So what I'd like to do in this talk is talk a little bit more about intelligent tutoring systems, like what sets them apart from other types of learning technologies. And then since this notion of adaptive instruction or personalized instruction can mean so many different things, I'd like to talk about the Adaptivity Grid, which is a framework that my colleagues and I have created to understand this notion of adaptivity better. And finally, I will come back to the intelligent tutoring systems and then talk about the authoring tools that my colleagues and I have made so that intelligent tutoring systems, as an example of adaptive tutoring software, can be built without programming. And this talk is based mainly on two papers that my colleagues and I have written that I've listed on this slide. Okay, but let's talk about intelligent tutoring systems. What is special about them? And let me just start by giving you an example. I gave you one already, the Algebra Cognitive Tutor, but now I'll show you what this looks like from the student perspective. So I'm looking at MathTutor, which is an open educational resource that my colleagues and I have developed, which is a website with intelligent tutoring software that is freely available for middle school teachers and students to use. And we're going to look at one problem of one of the tutoring systems on MathTutor. So this for American system, this is in 7th grade, and the students, this is what one of that problem looks at the beginning. So there's an empty table, there's an empty graph. The students will actually be using those tools to solve the problem, and there will be lots of help along the way from the tutoring system as they go. And I'm going to play this like in super fast forward mode. So way faster than any student can solve it, maybe way faster than any professor can solve it really. But just to give you the flavor of what this is like. Well, this is actually what it looks like at the very end. But now let's look at the steps of a student solving this problem with the help of the tutoring software. So the software will give feedback as we go. There'll be some messages at the bottom of the screen, and the system will update its model of the student's knowledge at the bottom right here. Okay, so ready, here we go. So this is going to be really fast, right? So red means wrong, green means right. So this is the student typing, gets feedback from the system. At the bottom, sometimes there is a message. The student works through the graph, there are more messages. The student's knowledge profile is updated, and now we're at the end. But this might take a student like 10 minutes. But the main thing the main reason I wanted to show you this is that there are many steps, and there's lots of help with the steps of the problem, not just at the end. And this kind of software you can actually build with these tools without programming. Here's another example, just to show you another example of a tutoring system. This one is for high school and college level genetics, built by my colleague, Albert Corbett. And as you can see, again, it's sort of elaborate problems that require quite an extensive reasoning process from the students. And we've in fact, built many more tutors. This is with the tools. This is only a small sampling. So just to show you that these kinds of tutoring systems have a rich history. In fact, my colleagues and I, about 20 years ago, created a company that is called Carnegie Learning that still exists. It's in Pittsburgh. And they sell curricula for middle school and high school math that have these intelligent tutoring systems in them as an important component that students use in the schools like twice a week. These curricula are used by about 500,000 students every year in the US. This is what you see here is actually an old article in the New York Times about 10 years ago where the New York Times reported on the use of the tutor in New York schools in the Bronx, in the middle school. So you see the old hardware that made you smile. So it still runs. Here's another example of software made by that company, just to show you that there are many examples. But here's the important thing. By now, there has been lots of research by many different people investigating whether the software actually helps students learn. And in fact, many researchers have even written meta-analyses, so studies reviewing the whole literature on these kinds of studies. And these generally have found in 4 meta-analyses that instruction that includes this kind of tutoring software tends to lead to better learning outcomes for students than other kinds of instruction that doesn't have such software. And in fact, one of the authors, Kurt Van Leen, who is a famous professor in the area of intelligent tutoring systems, went as far as to say that intelligent tutoring systems are nearly as effective as human tutoring, which we all know is a very, very effective way of instruction. So in other words, there's lots of evidence that this kind of software can help students really well. And just to dig into a little bit more detail of how this software actually works from the student perspective, let me show you slightly in close-up some interactions with Lynette, which is a tutor for equation solving, middle school, that we build in our lab. It's really a research tutor, it's not a commercial tutor. We've used it in many studies, and we typically see that students learn when they use this software, are much better at equation solving. So here you see some middle school students actually working with the system in one of our studies. But as mentioned, the key thing is that if we give students elaborate problems, it's important that they can also get some help along the way, not just at the end of the problem. So the system gives this feedback on the steps in red and green. And I understand that in Asia, red is actually a good color, if I understand this well. But in the US, red means wrong. So maybe we got it wrong. It's like a traffic light. So green means that the student did well. So for Asian use, we may have to change this in the software. The tutor also gives, in addition to feedback, gives hints. So there's a hint button or a help button. The student can always click the help button and then get feedback or get some hints from the system for how to solve the problem. And this is always available. And the hints might explain what to do next and why that's a good thing to do and how you could know that's the thing you should be doing and not something different. And I said these problems often have different solutions. This is very true in equation solving. So here we have one simple equation still, but even a simple equation can have many steps, first of all, and also many different variations. So this student was taking many steps, but here is another student, same basic transformations, but bigger steps, so it looks a little different. And a third student actually solved the same equation with different transformations. And for the software to be helpful, it should be able to recognize this different way of solving and follow along whichever way the student decides to solve these equations. So there has to be this flexibility built into the software. And so, as mentioned, a key form of adaptivity in this software is that there is guidance within problems. So I showed you many tutoring systems. Here is another one for equation solving. And the student can take many steps and always get feedback. This was actually me trying to make as many errors as I could make. So all the red things are errors in the tutoring system. But it's important to realize that in educational software, there isn't always help with the steps. So if we look at Khan Academy, for example, very widely used, I'm sure many of you are familiar with Khan Academy. Here is a unit on equation solving. And this is what it looks like for the students. Solve for B, then there is an equation that requires many steps to solve if you're a middle school student. And then the student can only enter the final answer. There is no help with the steps. There's no feedback. There is, if the student asks for help, the system will print out the step-by-step solution that you see here. With many steps, you can see there are many steps. But this is actually not that easy for students if you're really new to equation solving. And maybe the student was actually following a very different solution. So there is much research that shows that feedback and help with the steps is more effective for students than just at the end of the problem, like we're seeing here at Khan Academy. Another way in which intelligent tutoring systems are adaptive is that they support personalized problem selection. And one method for doing that is called cognitive mastery. And here the idea is so it's a form of mastery learning about which there is a large literature, which means that every student gets just the right amount of practice, but they have to demonstrate mastery before they can move on to the next unit. And the system makes sure that they get the right practice to reach mastery. And in order to make that happen in the software, it needs to keep track in detail what every student knows based on their performance with the system. This is built into the tools that I'll show you, but each system, this is easy to author, in fact, if you're building such a system. But so there is a way of breaking up the overall competency of solving this kind of problem into small knowledge components and mapping the steps to knowledge components. And with that information, the system then can keep track of the probabilities for each of those knowledge components that the students masters them. And behind the scenes, there is a Bayesian formula, and based on some simple assumptions about learning that has been used a lot. It's called Bayesian knowledge tracing, developed by my colleague Albert Corbett, that the system uses to calculate those probabilities based on the performance with the system. And then based on that, so that gives it a student model, as we call it, a model of what this particular individual student knows. And based on that, the system can then select tasks that are exactly what that student needs for those things that the student hasn't mastered yet. There's been some research evaluating whether that is actually better than one size fits all, than giving every student the same set of problems as we often do when homework, or at least in the United States, when we give students homework, everybody gets the same homework. Everybody has to do the same set of problems. But this research strongly suggests that students are better off with mastery learning, where every student might actually get a different set of problems that are geared especially to what that student needs. I've talked about two forms of adaptivity, but there are actually many forms of adaptivity. And a key assumption is that maybe we all share, that instruction is going to be most effective if it takes into account that learners are different, and of course that they're changing as they're learning. They gain knowledge, they gain understanding. But maybe it's less commonly realized that instruction also needs to take into account how students are similar in any given task domain. Like it may be true that in any given task domain, it's actually quite predictable what will be difficult for students. And it may be that the same thing will be difficult for many students. If you ask teachers what is difficult in equation solving, they'll tell you that certain things are quite difficult for most students. And so what may be different, though, is that students might experience these struggles not at the same time. Some students have more prior knowledge and may get there faster, for instance. And so I would say that instruction is adaptive to the extent that it takes into account how learners are different, that they change as they go, but that it also designed with a good sense for how learners are similar and of the similarities in the challenges that they experience in the given task domain. And of course, those are sort of very general words, but it does raise some important questions. Since there are sort of many different, students differ in many different ways. There's many different psychological variables that we could look at. And so that raises the question, what makes for the most effective adaptive instruction? Like how can we best tailor instruction to individual students? And also, even if we know that, we still want to be able to make instruction, make software that actually can be adaptive in those particular ways. So those are key questions in this talk. So to understand adaptivity, and having seen some forms of adaptivity, I thought it was useful to share with you a framework that my colleagues and I have developed that we call the Adaptivity Grid, to sort of map out a space of different forms of adaptive instruction. And it's this matrix that you see here, with two axes. The first one is what to adapt to, like what student variables should we be adapting our instruction to. And the other is what to adapt, like what elements of the instruction should we adapt, because in principle we can adapt so many different things. Like task selection is only one possibility. And we found it useful to have like 5 different realms of student variables to distinguish in this grid. Student knowledge and their knowledge growth, the way they go through problems, like what strategies and errors do we see when students solve problems, their individual affective state or their some motivational state or motivational variables, how they self-regulate their learning, and their learning styles. So these are sort of broad realms of psychology. You could probably imagine other variables, and they may be useful as well, but this was our starter set, so to speak. So that gives us this what to adapt to dimension, broken down into 5. And likewise, we break down the other dimension, the what to adapt dimension, into 3, based on sort of how frequently these adaptations happen, the time scale of the adaptations. So if the adaptations in the instruction, if the way the instruction is varied in response to student variables happens in the steps of problems, in how the system reacts to the student steps of problems, we call that step loop adaptivity or step loop adaptations. So here in the column on the right. But if the adaptations happen with respect to tasks, like which task the system selects for students, then we call it task loop adaptations. And this distinction between step loop and task loop is often made in the literature on intelligent tutoring systems, and is due to Kurt Van Leen, who first wrote about this distinction. Finally, if the designers of the system adapt the system after they've seen some data of students using the system, so they have built the system, students have used it, they've collected data, and then analyzed it, that may give them some insights into how the system, where the system is functioning well, where it's functioning not so well, and where their assumptions about students were correct, and where their assumptions about students may not be correct, and then they might update the system with the result that the system becomes more adapted to the student population as a whole. So that we call design loop adaptivity. And in some ways, all these forms of adaptivity are always driven by data about, sometimes by data about individual students, but oftentimes data about more students. And so we find it useful to look at adaptivity with this framework in mind. It's perhaps important to point out that even if you look in one cell, there is not one thing in it. It's still a broad set of things that is in each cell. It's still a broad class of adaptive mechanisms that we can see there. But nonetheless, it sort of helps carve up this broad notion, and notion about which there are sometimes misunderstandings of adaptivity or personalization, and we can be a little more precise in what we are talking about when we're discussing those notions. And I showed you, as I illustrated the intelligent tutoring systems, I talked about 2 main examples of adaptivity that were embodied in the software, namely sort of guidance with the steps of problems, following student strategies and responding to students' errors in adaptive ways. So if we were to place that form of adaptivity in the grid, I would say it ends up in the step loop column, because this is about how the system reacts to student steps. And it ends up in the row on strategies and errors, because the system is reacting to the strategy that the student is using to solve the problem, or is reacting to specific errors. So I would say this step-level guidance that we see in many intelligent tutoring systems can be placed here in the grid. The second thing I talked about was this cognitive mastery. So the individualized task selection based on individual student knowledge growth. And if I were to place that in the grid, I would put it here, in this cell here. It's a task loop adaptation because it's about problem selection, and it's an adaptation based on student knowledge growth. So that's why it's in the first row. But now you might see, well, we still have these 13 other cells. So what about those cells? And we were curious too when we were working on this. So what we did was look at the literature, find many papers, and in particular, we were interested in papers that tested empirically. So these were not technical papers necessarily, but papers about studies in classrooms and studies with systems about student learning. And in particular, papers that tested whether a particular form of adaptivity made the system more effective. So the best papers we could find had compared student learning with 2 forms of instruction, and where the only difference between those 2 conditions was the particular type of adaptivity. And so here, this is the same grid, although it looks a little different, but it's literally the same grid with the 3 columns and the 5 rows. These are the papers that we looked at, but now sorted into this table. And we were actually quite surprised to see how many papers there were and how many of the cells were covered. And this was about 5 years ago. So this tells you that the research in this area has looked at many different forms of adaptivity. This was a bit of a surprise to us, frankly, even though we were sort of right in the middle of this research community, we were still surprised when we looked at this very systematically. But more important, though, you might ask, well, what did these studies say? What were the results, right? It's nice that there are studies, but we do want to know what they say. What do they say about the value of adaptivity for student learning? And that's shown here in this version of the grid. So a check mark here in this grid means that there was at least one study that showed that particular type of adaptivity had been shown to enhance student learning. So instruction with that form of adaptivity led to better learning outcomes for students than the same instruction, but without that form of adaptivity. And you can see there are many check marks. That, again, was a bit of a surprise to us when we were doing this. But so the literature provides quite a bit of evidence for different forms of adaptivity. The one tilde is where there were some studies showing the value of that form of adaptivity, but there were many, many more studies that actually did not show any value. So that's maybe a bit equivocal. But if you look across the grid at the trends that we see across the rows and columns, you see that actually the literature had reported on quite a few of these design loop adaptations. So this is the left column of the table. And remember, so those are design loop adaptations are when the designers of the system use data acquired when students use the system to analyze how the system is working, how students are learning, and then change the system in ways aiming to make it better. So that's design loop adaptations. The designers are doing the adapting. And we found many studies, and the studies tended to have positive results. We also found points B and C here that there was strong evidence that adapting to students' knowledge or their knowledge growth and adapting to students' strategies and errors was effective. And maybe that was less of a surprise given that this is something that intelligent tutoring systems have traditionally done. But nonetheless, it was good to see that confirmed. On the other hand, we did not find much evidence that adapting to students' learning styles, which are defined as sort of broad preferences for learning in a certain way, like visual versus verbal, or sort of being holists versus serialists, like whether you prefer to sort of have a big picture first or sort of go very much in order. Whether instruction that adapts to those kind of preferences from students actually leads to better learning. It turns out that the evidence is very, very thin. Many studies that did not find a result. Well, we also found many studies, which is not among the trends, but it should have been, many studies that show that adapting not just to the cognitive factors like knowledge and errors of strategies, but also to affect motivation and self-regulation in systems can lead to better learning outcomes for students. And finally, this is hard to show in the table, but we also found interesting studies that showed forms of hybrid adaptivity, I would call. So by that I mean that the adaptations are made in response to multiple student variables. So for instance, when selecting a new problem, you might look at what the student knows, what the student has learned so far, but you could also look at their affective state at that very moment, if the system is assessing the student's affective state. And so you might, to students with the same knowledge, you might give a harder problem if they're engaged, but maybe an easier problem if they're frustrated. So that's what I would call a hybrid strategy, because it combines cognitive factor or knowledge with affect, so different variables. And as we did this study, we saw many, many interesting studies that Marcia Lovett and others redesigned a statistics course, an online course based on analysis of the students' knowledge growth, so using data. So this was one of these design loop adaptations, and found that the course was spectacularly improved. Like students learned way more in half the time. Like when does that ever happen in educational research? So illustrates the power of design loop adaptations. Salden et al. Studied this what is the right combination of worked examples and problems. So there is much literature that says that you shouldn't just give students problems, they also should actually study quite a large number of examples. And in this study, a method was developed that the number of examples that the students would see before they would transition to problem solving was made adaptively based on how well students were explaining those examples. And so different students might see different numbers of examples before they went on to problem solving. And that turned out to lead to better learning than either just problems or making a fixed transition, like the same number of examples for everybody. Sidney DeMello et al., who created a dialogue tutor, and he found that if the dialogue tutor responds to whether students are confused, bored, or frustrated, so their affective state, and react with empathetic language, like language trying to be understanding of this, how this is for the student and understanding of their feelings, led to better learning for the students with low prior knowledge. So this is another example of reacting to student affect. And finally, Walkington and Bernanke, in an interesting study with a tutoring system for algebra, they try to tailor the cover stories based on the student's personal interests. So if a student was interested in movies, then the algebra problems would talk about movies. The math would be exactly the same. But a student who was interested in sports would get the same problem with the same math, but with a story about sports. And you might say, well, what does that have to do with learning math? But amazingly, the students, when they got these personalized cover stories, learned better in math. And in fact, this difference persisted even later in later units of learning, even when the cover stories were no longer personalized to their personal interests. So this is just a sampling of studies and a sampling of ways in which adaptive instruction has been shown to be effective in this literature. As I said, I find this very interesting. This is really what the field of AI in education is about. They do these kind of studies and aimed at sort of uncovering the secrets of adaptive instruction. But what about authoring? Like I promised you to talk about authoring. And so can we now go back to authoring tools? So now we have a sense for adaptivity is a broad notion and can mean many different things. How can we author adaptive software? And does it need to be very complicated AI, or are there actually ways in which we can create these systems that are not so difficult? So I'm going to show you the cognitive tutor authoring tools, which I would argue is a form of open and innovative educational resource. So here you see CTAT, the different tools that I'll talk about in a moment. We have documentation online about CTAT. We have our website, we have our wiki. And as mentioned before, we have built many, many different tutors with CTAT that have been used in classrooms, and many of them have been shown to help students learning. And just to give you a sampling here, these are tutors in a topic in machine learning, in genetics, that one you saw already, in college-level statistics, in programming, in chemistry, in middle school mathematics, elementary mathematics. And then at the bottom left is a tutor for business mathematics that is integrated with Google Sheets. So the students are working in Google Sheets as they would if they were doing some business analysis with spreadsheets, but they get feedback from a CTAT tutor that is hooked up in the back. That, of course, did involve programming to actually hook the tutor backend into Google Sheets. But it shows you one way of building tutors is to add tutoring to an existing problem-solving environment. As mentioned, we have worked on these tools for a very long time. One of the goals when we set out to do this was to make tutor authoring easier. So even 15, 20 years ago, it was known that tutors could be very effective, but there was always this problem that tutors were hard to build. And we did some studies. It's very hard to get very precise data, but we found some evidence that with these new tools that we made, with the CTAT tools, tutor building can be 4 to 8 times more cost effective than the historical estimates of tutor development cost. These tools have by now been used very widely by at least 750 authors. That number is probably a bit low. And as I mentioned, dozens of tutors have been built, have been used in classrooms, in many research studies. So usually these were tutors built for research, not so much for regular use in classrooms. And all in all, about 44,000 students have used these tutors. And one thing that made it possible to build tutors without programming is that as we were working on these tools, we created a new kind of tutor, a new paradigm for tutoring that we called example tracing tutors. And this was critical. Like before, tutors had to involve AI programming, and that was one of the reasons that they were hard to build. But with this new way of implementing tutors, it was possible to create them without programming. And so each example tracing tutor has two main components. A tutor interface, so this is where the student solves problems, and this needs to be designed and implemented usually separately for each unit, because the reasoning steps in different problems are usually different, so you need a different interface that shows the reasoning steps. And then the second main component is the tutor backend, which is here, a key part of that is a behavior graph, which is the tutor's main knowledge representation that captures in the form of this graph problem-solving knowledge, like how do you solve these kinds of problems. And so these are the two things that when authoring a tutor you need to create, the tutor interface and the behavior graph. For the tutor interface, we provide a drag and drop editor so that lets you edit the interface basically as if you were working in PowerPoint, let's say, to create a diagram. Although if you know HTML and CSS and you like coding in HTML and CSS, that's entirely possible and probably a good solution for you. And then these behavior graphs can be recorded and edited with a specialized tool that we call the behavior recorder. And I thought I'd illustrate this in the domain of fraction addition. And not because I think you will be very impressed with a tutor for fraction addition, but it's easier to illustrate how the tools work in a simple domain. And so simple is good in this respect. And actually, as it turned out, even building a good tutor for fraction addition, where the student can solve the problem in many ways, is not that easy with the tools. Because we want the tutor to recognize many different solution paths. So here, in one fraction addition problem, the student might use 24 as the common denominator, but the same problem could be solved with other common denominators. Here it's 48, 72, or even 336. Is that good from a pedagogical point of view? You may be the judge, but it actually would seem that if a student had the idea to do this, the software should not say it's wrong, so it should let them do it, I would say. So we want the tutor to be able to recognize these different solutions. Again, we wanted to give feedback on steps, not just on the final answer. That would be much easier to build, but not as good for students. And so the tutor will give feedback. Sometimes it might even give a specialized feedback message when it recognizes a frequent error, such as adding the two denominators instead of just using the common denominator. So there might be a specialized message that the author has. We want the tutor to give next step hints. So students should be able to press the hint button at any time and then get some feedback as to what to do next. So this is about finding a numerator when we're trying to make the fractions have a common denominator. And usually there are sort of multiple levels of hints available that become increasingly more specific, and then the last level usually gives the answer for students. And if we're trying to follow students along different solution paths, then of course those hints should also be specific to the solution path that the student is following. So here, if the student was solving this problem with denominator 12, which then the answer will be in the lowest terms when they have added the two fractions, and there's no need to reduce it further. So if the student asks for a hint at that point, that's what the system should say, and that's what happens here. But with 24 as the denominator, there is still the step of reducing this to lower terms, and if they use some other common denominator, that step also needs to be done, but now the numbers are different. So we want the tutor to be sensitive to all those differences. Finally, we want the tutor to track students' knowledge growth. So we need to divide up the skill of fraction addition into these smaller knowledge components, and so that the tutor can actually track those knowledge components. So let's see, so those are just laying out what it is that we actually want to author, and now we'll talk about, well, how can this be done with the tools? And so I'll give you a little flavor of that, only the basics, hopefully enough to understand the big ideas. So there were these two components that are important if we want to build a tutor, the interface and the behavior graph, the tutor backend. So, and for the interface, we have this dedicated interface editor that we built, shown here. So let's say we're going to use that to build that fraction addition tutor now. We need to log in, so I logged in. Now I'm logged in. So on the left here, you see a great list of interface components. So these are components that we made, interactive elements that you can arrange on the canvas here. There is on those, in the CTAD wiki that I pointed you to, there is documentation. And those can be used to design these interactions that students will have that will support their reasoning process in the tutor. Well, let me actually save the interface. Let me make this a little bigger. And then let's start by laying out the interface. We'll start with this fraction addition label at the top. Then we'll add a hint button at the bottom. We also need a done button. Every tutor needs to have a done button. So we'll pull that off the palette as well and then show it here. Each tutor needs a hint panel. So we also, in the set of components, there is this hint component. We want to make that the right size, of course. And the same for this panel where the skills are displayed. So there is also a standard component for that that we take off the panel, that we add here. And now we can basically lay out all the fraction component in the interface, which means we have text inputs, and we can just build up the interface the way it'll eventually look. So we need fractions. These components need to have names. We'll add some other text inputs. We'll copy them. And eventually, we have basically made our interface. So here it is. So that gives us one piece of the puzzle. We have the interface. But we still need the tutor backend, the interface, but we need the problem-solving knowledge for the tutor. So we need a second tool. So on the left, you see the interface. We've launched this. It's running in the browser. On the right is a tool called the behavior recorder. So this is what we're going to use to record a behavior graph. So the author is going to first set up the problem. So 1/4 and 1/6, that needs to be typed into the interface. Then in the behavior recorder, we can say, okay, let's start our problem here. Let's create the start state. We need to give the problem a name. And now the author can start demonstrating the solutions. So the author just does the steps of the problem. The behavior recorder is in demonstrate mode, meaning it'll just record those steps. So the author will just type solution steps. So here's 12. And then each step is recorded in this behavior graph with one link in the graph per step. So as the author types the solution. So just a form of recording what the author is doing. There also needs to be a click on the done button at the end. So now we have this graph. We have an interface and we have a graph. So, and I said the two components are interface and a graph. So we already have a simple tutor at this point. Like, it's not complete. We still need to do other things. But it already functions as a tutor. So as part of the authoring process, I could now start testing the tutor as if I was a student. And that means I need to change the mode in the behavior recorder. So before we were in demonstrate mode, the behavior recorder records, but now I'm in test tutor mode. And that changes things because instead of recording what's going on, the tutor will now use the behavior graph to evaluate the problem-solving behavior. So let's just test the tutor. Oh, actually, one more thing I need to do is I need to tell the tutor that it can be in unordered mode so that the student doesn't have to follow the same order of steps. I think it's better if there is freedom. So I'm just setting it to unordered mode. And now the student can go through the steps in any order. And let's see what that looks like. So I'm typing here the numerator, and that's the same as in the graph, so it gets the answer right. Same for the denominator. If I type a number that's not in the graph, then it gets feedback that it's wrong. And we can already get some hints too, although it may be hard to read, but the hints just say what number to type. So not very good hints, but something that works. And so we already have the basics of a tutor. And then when the student clicks the done button, the system says, congratulations, you're done with this problem. So that's my brief demo. So I showed you some of the basic ideas behind CTAD and example tracing tutors. So we can build an interface through drag and drop. We can use programming by demonstration. So that's this process of demonstrating behavior in the interface that then gets recorded to create the behavior graph that captures problem-solving knowledge. And then the example tracing algorithm will use the behavior graph to follow along with the student's solutions. And now I showed you a simple tutor. It doesn't have all the features of the tutor that I demonstrated up front. As you no doubt notice, because it doesn't have the flexibility to recognize multiple solution paths. You would like it to have better hints. We'd like it to trace the student knowledge growth. We'd like it to, we want to create many problems. This was only one problem, but we want to create many. And maybe we also want other forms of adaptivity that are in the adaptivity grid that I just talked about. So those things are not in my demo, but they can be done with the tools. For instance, if you want to be able to recognize multiple strategies, then you should make sure that your behavior graph actually records those strategies. So you need to record more paths. And just to show you what, in the end, this graph looks like if you did all the steps. It's a little, as I said, fraction addition is actually deceptively complicated. But this is what this graph ended up looking like. So if we return to our adaptivity grid to see what kinds of adaptivity we can author with those tools, I would say it's the same tool that we illustrated with the earlier tutors. So adapting to student strategies and errors in the step loop and adapting to their knowledge in the task loop. And that's the main kinds of tutoring functionality, of tutoring behavior that you can do with these tools without programming. There are maybe some other forms. And I should also mention that as some other tools, so we often use the data shop. This data shop, as mentioned, is this open repository for educational technology data. And so each tutor that you build with CTAT will automatically log to the data shop, which is wonderful because the data is always full of insights that help analyze what students are doing. Furthermore, we have worked a lot on making it possible to embed these tutors in a variety of learning environments, including MOOCs, including online courses. So they can be embedded in web pages, they can be embedded in TutorShop that I mentioned, our dedicated LMS for tutoring systems, but they can also be integrated in many learning management systems using existing e-learning standards such as SCORM or LTI, and we have even built some custom integrations into OLI, which is the Open Learning Initiative at Carnegie Mellon, that is a platform for building online courses that is also open. And we have integrated tutors in edX, for instance, in a MOOC called Big Data in Education. So we integrated CTAT tutors through LTI, which makes it easier to apply them in different contexts. So to wrap up, I've talked a lot about intelligent tutoring systems and the way in which they adapt to learners, and about all the evidence that has accumulated over the years in many research studies that these systems can be highly effective in helping students learn. I've shown you the adaptivity grid, which I hope is useful in thinking about things like personalization, adaptivity, which are such broad terms. It may be more fruitful if we can have a framework that lets us talk about adaptivity in a sort of more precise way, and that's what this is meant for. Using the grid, the adaptivity grid, we also saw that there is actually in the research literature many evidence that many forms of adaptive instruction can enhance learning outcomes. And I hope that my simple demo has convinced you that CTAT can help us build adaptive tutoring software without programming that have at least some of the really important forms of adaptivity for students. And these tools, the CTAT tools, are, as I said at the beginning, they're open, so they can be downloaded and used for free for non-commercial purposes. And they are innovative, and I really hope that they'll find uptake and bring adaptive learning to many learning environments, that these techniques used in tutors that have been successful but haven't spread as widely as one would hope, that they find sort of greater acceptance and many more people who want to build them. So thank you very much.
Thank you very much.